Alright everyone, so let's start practicing. We have basically finished our electricity and magnetism content, and let's practice this last piece by just doing a few questions together. Alright, remember that you can always pause the video, so you can always go through the questions slowly. If you need more time, you can always pause and check your answers and anything. Okay, so let's start this. Okay, so this is a quite interesting problem. It's an application of both electric fields and magnetic fields at once, and also some of the forces, right, which will have to be zero. Now let's see. So we've got an electron. So we have an electron here, which is being shot. It was somehow accelerated and shot in that direction. So it's going to get into an area in which there is a magnetic field which is going into the board. That's why we see a cross. It's because it's going in the board. So if it was an arrow, we would be seeing the butt, right, the tail of the arrow. And also there is another field which is going downwards. This is an electric field. Now let's observe. This is an electron. So before we look at any of the numbers, let's understand this problem. So this is an electron. It's a negatively charged particle, right? It has negative charge. If it was positive, if a positive charge came here, it would fill this field, and then it would deflect downwards. It would tend to feel a force downwards if it was positive. Remember, the arrows, they represent from coming the direction at which the positive particle would go. So here, if this is a negative charge, because of the electric field, it would tend to go up. So let's draw a free body diagram. So there should be some electric force pushing electric force. There should be some electric force pushing that particle upwards. Also, because of the magnetic field, remember, I try my best here. Okay. So this and right. Sorry. Let's try again. So let's say that I have this, and this. Okay, so this is the right hand rule. Okay, just ignore my terrible drawing skills. Alright, so what is happening here is, well, basically this is the direction of your particle, right? This is the direction of your field, and this would be the force that particle would feel if it was positive. So this electron is going to suffer from a field which is going into the board. So if B is going into the board and the speed of the particle is there, see, B is into the board. This is the velocity of the particle. So you would feel a force upwards, right? If it was a positive particle. However, it's negative. It's an electron. So the force will be the same magnitude but opposite direction. So there should be some force. I'll call it Fm, magnetic force. Right? So there we go. Now, what is the whole point of this question? Well, this force is constant because it only changes with the field, which is constant, and the particle itself, the charge itself, which is also constant. An electron is not going to lose charge, right, or gain charge out of the nowhere. However, our magnetic force changes with speed. So the faster our particle is moving, is traveling, the faster the force, the stronger the force. So if you remember, we do have an equation for electric field and also an equation for magnetic field. So the electric force, right, and also the magnetic force. So the magnetic is fresher, we have just dealt with it. So it's B, which is your magnetic field, Q, which is the charge, V, which is the speed of your particle, and the sine of the angle between the field and the particle. This is because it's actually not a simple product, it's actually something else that we don't want to worry here in the physics course, right? Now, if you remember, the definition of electric field is force over charge. So since the field is force over charge, we can just multiply our field by the charge, right? And just to make things consistent, I will also use capital Q. Alright? So we have, so let's move this up. Okay, so that value, that force, magnetic force, might change. And we have to look for what is the velocity that makes those the same. Because if the particle is moving at constant speed, right, there's no net force. So we want the net force to be zero. So if the net force is zero, Fe, the electric force, will have to be equal to the magnetic. The vectors, we have already thought about them, so they're just pointing on the opposite direction of one another. Now the magnitudes, they will have to be the same. So this is EQ, which is equal to BQV sine of the angle between them. Now notice that's the speed of the electron and the field, they are perpendicular. So this is 1. Right, so this is 1. So if we rearrange, well, we can also cross out the charge. So we would have simply that the velocity would be the ratio of the electric field and the magnetic field. That's pretty awesome, isn't it? If you put numbers in, this should be, I've just put in my calculator, so 1.52. Now since this is a velocity, right, it's going to be something meters per second, but that's times 10 to the power of 7 meters per second, which is quite remarkable. That's more than 5% the speed of light. So that's actually pretty fast. Alright, so take a look at this problem here. It's the second situation in which we have an effect of a magnetic current which is produced by some current which is flowing, a magnetic field, which is produced by a current which is flowing through a wire. And how does it interfere with other magnetic fields which are already happening there? So we've got a straight wire. It's a uniform magnetic field, so it's constant, it doesn't change. Now the current in the wire is I, and the wire is at an angle theta to the magnetic field. The force per unit length on the conductor is F. Determine the magnetic field strength. So if you want to pause and try it for yourself, that's fine. I will just move forward. So F is defined as force per unit length. So since this is a magnetic force, this is going to be magnetic force per unit length. So the magnetic force is B L I sine of the angle between those, right? That's the equation that we have for current. We have one for current, one for charge. The one for charge, you change this for charge and this for the speed. So since this is force per unit length, right? So length over length, and then I can cross out length on top and below. So that would be B I sine of theta. I cannot assume anything regarding theta because it's not said that it's a 90 angle, it's a 45, whatever. So I have to just keep it there. So since the question is asking us for B, the magnetic field, we'll just rearrange this equation and make B our subject. So that's F over I sine of theta. And that's it. As simple as that. Okay, so let's go for a numerical problem now. So a straight wire of length 0.75 meters carries a current of 35 amps. The wire is at right angles to a magnetic field of strength 0.058 Tesla. Calculate the force on the wire. Alright, so let's write down what we know. First thing, we know the length. So the length is 0.75 meters. Now I also know the current. So my current is 35 amps. We know that the wire is at right angles to a magnetic field. So the angle between them, 90 degrees. Right? The magnetic field, let's say the wire is going that way. That's where our current's going. And the field is, let's say, that way. That could be it. It doesn't mean that it is, but that's one of the possibilities. So this could be your current I. Now also the magnetic field strength B is 0.058 Tesla. So if we look at our physics data booklet, we'll have that the magnetic force, which is what we're looking for, is going to be B I L sine of theta. So everything is in SI units, so I don't have to worry about conversions. So this is basically 0.058 times 0.75. I've put the length first. Current 35 amps times, no, sine of 90, this is going to be 1. So times 1. I don't have to do that, right? So if you put all of those numbers into your calculator, you should, if I'm not mistaken, get something around 1.52. Okay, so since this is a force, Newton, and approximately 1.5 Newton if we're keeping up to two significant figures. Alright, that's simple enough, isn't it? Okay, so that's probably the last practice question we're going to do regarding electricity and magnetism, besides obviously the higher level content. So we've got an ion with charge plus 3.2 times 10 to the negative 19 coulombs. So let's start writing things down. Okay, so charge, so it's positive. That's important because it's going to follow all of our conventions for the direction of field, right, where the force is going to drive it towards. Alright, so the mass of that same ion is 2.7 times 10 to the negative 26 kilograms. So yeah, very small charge, very small mass. It's moving due south, so it's moving south. Okay, let's say that we're looking from the top. Okay, so south is down, and our magnetic field strength, it will enter a magnetic field strength of 4.8 times 10 to the power 3. No, sorry, that's the speed of the particle. That's the speed. So it enters a field, so this is the speed of the particle, meters per second. That's the magnitude of the speed of the velocity. And the field, now we're talking about the field, 4.6 times 10 to the negative 4 Tesla. So we have everything that we need, isn't it? Directed downwards towards the ground. So if we're looking from the top view here, it's towards the ground. So the field would be going down. Okay, that's our representation. So if you remember your right hand rule, right, your index finger would be pointing down, right? Your other fingers, like the middle fingers and all of those, would be pointing down. So this is the direction of the velocity. This would be the direction of the field, and your fingers, those ones here that we cannot see because they are hidden, and this would be the force for a positive particle. So since this is positive, that's actually the force. That's actually the direction where it's going to accelerate. Alright, so determine the force acting on the ion. So we already know the direction. The direction is, so if this is south, this would be east. Right? Now let's calculate the magnitude. So force, since this is a magnetic field, B, Q, right, L, well, no, sorry, speed one. So we have two equations. We have this one, sine of the angle. In this case, both signs will be 1. And we have this other one, which is, So we have two equations. I don't have the booklet here, that's why I'm getting all of those wrong. So that's B, L, I, and sine, which will be 1. And we also have B, Q, V, sine, which sine will be 1. So if we notice what we have here, we have charge, we have velocity, we have field, we have everything that we need. We don't even need the mass. The mass could be perhaps something for a follow-up question. We could ask, okay, so what's the acceleration? But for the force, this is the equation that we're going for. So BQV. So B, that's our field, so that's 4.6 times 10 to the negative 4. Everything is in SI unit, so I don't have to, besides the mass. Everything else is in SI unit, so I don't have to, even the mass is in kilograms. I thought it was in grams. So we can just multiply them. So BQ, Q here is 3.2 times 10 to the negative 19 times our velocity, which is 4.8 times 10 to the power 3. So if we put all of those numbers up in our calculator, it would be around 7.065, so 0.66 times 10 to the negative 19. We would expect this to be a very small number because this is negative 4, this is positive 3, this is negative 19, so this is a very small number. Now up to two significant figures, it would be around 7.1 times 10 to the negative 19. Since this is a force, newtons, right? And that's it.